Boundary conditions. This is very important topic. Suppose, what is the meaning of this boundary conditions is, suppose this is a region, free space, or suppose this is some region in free space. This is a region. Suppose in this region there are two different medias. This is media 1, this is media 2. So it has some properties epsilon 1, mu 1, sigma 1. It has some properties epsilon 2, mu 2, sigma 2. That is two different types of properties. That is, if a region is separated by two different medias, suppose a electromagnetic wave is propagating, that is from medium 1 to medium 2. Then the conditions the wave must satisfy at the boundary. The conditions the wave must satisfy at the boundary are called boundary conditions. So we can say the condition that the field must satisfy at the interface separating the media, separating the two media is known as or called as boundary conditions. Boundary conditions. So here we will discuss for different types of media what are the boundary conditions. I am not going here for the derivation of the boundary conditions, just I will give the boundary conditions and we will work out some problems how the boundary conditions satisfy. Here suppose the total electric field is divided into two components, Et plus En, where Et is tangential component to the interface, En is normal to the interface. Suppose this is the interface. So any E, suppose this is electric field, is divided into two parts. One is a tangential part and one is a normal part. So the resultant is E. So Et is the tangential to the interface. En is normal to interface. Similarly, magnetic field also there are boundary conditions. We will discuss later when we are discussing magnetostatics. So till here we are discussing electrostatics. That's why I am dealing with only E, electric field. So it is divided into two components, Et plus En. We will see first dielectric boundary condition. Dielectric boundary conditions. That is, the two medias are dielectrics only. That is, this is media 1, media 2. So this is dielectric with the properties epsilon 1, mu 1. This is also medium is dielectric with the properties epsilon 2, mu 2. Then what are the boundary conditions? So suppose this is electric field in dielectric medium 1, this is electric field in dielectric medium 2. So E1 I can write E1 tangential plus E1 normal. Similarly, E2 I can write E2 tangential plus E2 normal. The first dielectric condition to satisfied is E1T is equal to E2T. E1T is equal to E2T. This is the first dielectric condition to satisfy at the interface. That is, the tangential components of E are same on both sides of the boundary. Same on both sides of the boundary. That is, suppose this is E1, this is E1T, E2T, suppose this is E2, E2T, E1, E2N. So E1T is equal to E2T. That is the first boundary condition to be satisfied. So here I am not going for the derivation. We can derive this one. So you can refer any standard textbook for a standard derivation. So just to remember the boundary condition. Tangential component are equal. That is, the tangential component undergoes no change on the boundary and is said to be continuous across the boundary. So tangential component is continuous across the boundary. Continuous across the boundary. So E1T is equal to E2T. So E1T I can write epsilon 1 D1T because E is equal to epsilon D. Sorry, D is equal to epsilon E. D is equal to epsilon E. Therefore, E is equal to D by epsilon. So this is D1T by epsilon 1 is equal to D2T by epsilon 2. So once if you know electric field, then you can calculate flux density. Electric flux density you can calculate. This is the boundary condition in terms of flux density. D1T by epsilon 1 is equal to D2T by epsilon 2. Here they are not equal. D1T is not equal to D2T. That is, dt, that is electric flux density, undergoes some change across the interface. Hence, dt is said to be discontinuous across the interface. Since d1t is not equal to d2t, some different values. So some change, that is if it moves from medium 1 to medium 2, it undergoes some change. That's why it is discontinuous. The second boundary condition is d1n minus d2n is equal to rho s. d1n minus d2n is equal to rho s. d1 is normal component in medium 1, d2n is normal component of flux density in medium 2, rho s, where rho s is the charge density on the boundary. That is, so this is a boundary. This boundary has some charge density rho s, then d1n minus d2n is equal to rho s. Suppose if rho s is equal to 0, d1n is equal to d2n, then it becomes continuous. d1n, that is electric flux density, becomes continuous if charge density is 0. Otherwise, d1n minus dt(n) is equal to, the difference is rho s. So this is a secondary boundary condition. Suppose conductor dielectric boundary condition. Conductor dielectric boundary conditions. So this is conductor, medium 1 is conductor, medium 2 is dielectric. Medium 2 is dielectric. So conductor means perfect conductor. I am assuming sigma is equal to infinity. E field is 0. E field is 0. We already discussed. In a conductor, electric field is 0. So implies D is equal to 0. D is equal to 0. That is here E1t is equal to 0. Dielectric is epsilon 2. Property is some epsilon 2. E is equal to E2 is equal to E2t plus E2n. E1 is equal to here E1t plus E1n. But E1t is equal to 0. E1t is equal to 0. So what are the first boundary condition? E1t is equal to E2t. So the above what are the discussed boundary conditions are valid for all. E1t is equal to E2t. Implies E2t is also equal to 0. E2t is also equal to 0. So here E1 entirely becomes E1n. Here E2 entirely becomes E2n. Only normal components exist. What is the secondary boundary condition? D1n minus D2n is equal to rho s. Suppose rho s is equal to 0. Rho s is equal to 0. D1n is equal to D2n. Implies epsilon 1 E1n is equal to epsilon 2 E2n. Epsilon 1 E1n is equal to epsilon 2 E2n. Since this is a perfect conductor, E1n is also equal to 0. E1n is also equal to 0. Then what happens? E1n is equal to 0 means E2n is equal to also 0. If rho s is equal to 0, E2n is also equal to 0. Implies E2n is also equal to 0 if rho s is 0. Suppose if rho s is not equal to 0, then what happens? Then D1n minus D2n is equal to rho s. Epsilon 1 E1 minus epsilon 2 E2n is equal to rho s. E2n is equal to rho s by epsilon 2. So we have to consider only magnitude. E2n is equal to rho s by epsilon 2. If rho s is not equal to 0, then E2 is equal to rho s by epsilon 2. Rho s by epsilon 2. So only electric field component exists in dielectric. That is normal component. If rho s is not equal to 0. Suppose if rho s is equal to 0, then both fields are zeros. That is E1 is equal to 0, E2 is equal to 0. So like this, we can analyze the boundary condition. Now, we will discuss a problem on this boundary condition. The problem is two extensive homogeneous isotropic dielectrics meets on plane z is equal to 0. Plane z is equal to 0. For z greater than or equal to 0, epsilon r1 is equal to 4. And for z less than or equal to 0, epsilon r2 is equal to 3. A uniform electric field E1 equal to 5ax cap minus 2ay cap plus 3az cap kilovolt per meter exists for z greater than or equal to 0. Z greater than or equal to 0. Find E2 for z less than or equal to 0. So this type of problems are very important. We will see how to solve this type of problems very easily. First of all, draw a rough diagram to analyze the problem more clearly. Here, two extensive homogeneous isotropic dielectrics. Here homogeneous, what is the meaning of homogeneous? Homogeneous medium means properties are same everywhere. The properties are same everywhere, then it is a homogeneous medium. Isotropic means same direction. The field exists in a same direction. Dielectrics meet on plane z is equal to 0. Suppose this is z is equal to 0 plane. This is medium 1, this is medium 2. So this is z less than or equal to 0, this is z greater than or equal to 0. Here they are asking so here z greater than 0, so consider this as medium 1 and this as medium 2. This is medium 1 and this is medium 2. Here it is given for z greater than or equal to 0, epsilon r1 is equal to 4. So epsilon r1 is equal to 4 here. And for z less than 0, epsilon r2 is equal to 3. So a uniform electric field E1, so this is E1 in medium 1 exists for z greater than or equal to 0. Find E2 for z less than 0. So we have to calculate what is E2. So we know that I can write E1 as E1t plus E2 E1n, some tangential component, normal component. So E1t plus E1n is equal to, E1 is already given, 5ax cap minus 2ay plus 3az kilovolt per meter. That is, in this entire electric field equation, electric field, there is a tangential component and normal component hidden. So we have to find what is the tangential component and what is the normal component. How we can find that is, here it is given z is equal to 0 plane. So z is equal to 0 means xy plane. Z is equal to 0 means xy plane. So xy plane, what is the normal component to xy plane? Az. The normal component xy is Az only. So this Az part is normal component, the remaining part is tangential component. Therefore E1t, the tangential part is 5ax minus 3ay, E1n is equal to 3az. So this is a normal component because here it is given z is equal to 0 plane. Z is equal to 0 plane means xy plane. What is the normal component xy plane? Xy plane, obviously az is a normal component xy plane. That's why this 3az component is normal component, remaining is tangential component in the given electric field. So E1t is equal to this much, E1 is equal to 3az bar. So like this we can divide tangential component and normal component. So now we have to calculate E2. E2 is equal to how much? So E2 is equal to E2t plus E2n. So I have to calculate E2t and E2n. Then the problem is solved. So I am applying first boundary condition. Boundary condition 1. Boundary condition 1. What is the first boundary condition? Tangential components are continuous. That is E1t is equal to E2t. So half of the problem is solved. E2t is equal to, then E2t is equal to E1t. E1t is nothing but 5ax minus 3ay. So half of the problem is solved. Only I have to calculate E2n. So apply second boundary condition for that to calculate E to n. Secondary or second boundary condition. Second boundary condition. So what is second boundary condition? D1n minus D2n is equal to rho s. Here they didn't mention anything about rho s, where rho s is a charge density on the plane. They didn't mention anything in the problem. So rho s you have to consider as 0. Rho s you have to consider as 0. So rho s 0, that is D1n is equal to D2n. That is epsilon 1 E1n is equal to epsilon 2 E2n. I have to calculate E to n. So E to n is equal to epsilon 1 by epsilon 2 E1. So where epsilon 1 is epsilon naught into epsilon R1 by E2 is epsilon naught into epsilon R2 E1n. So epsilon naught epsilon cancels. So epsilon R1 by epsilon R2. Epsilon R1 is given 4. Epsilon R2 is given 3. 4 by 3 into E1n. So E1n is 3 AZ bar. So 3 cancels. That is equal to 4 AZ bar. 4 AZ bar. So E to n already I calculated. Therefore, total electric field E2 is E2T plus E2n. So E2T plus E2n. That is equal to 5AX minus 3AY plus 4AZ kilovolt per meter. So like this you can calculate the electric field. Very simple. Because half of the solution is already in the given problem itself. That is the tangential components. So if you differentiate the tangential component and normal component, then half of the problem is solved.